Hello everyone, welcome back to our engineering mechanics dynamics class. Today we're going to solve the second example of Newton's second law of motion that we're working. And in this problem we're going to involve a spring, Hooke's law, where you have a spring constant. We're going to apply that concept, and also in Newton's second law of motion we're going to use tangential and normal components. So let's see what's the problem. So our learning objective for today is to solve a problem that deals with force and acceleration, meaning we have to use the Newton's second law of motion, and we're going to use normal and tangential coordinate system to solve the problem. So in this example 2, we're going to apply the Newton's second law of motion because it will be related to force and acceleration, and then we'll determine the normal force and acceleration. And like always, the image from the spring, you can see that we're going to use the problem going to involve a spring, and we have to solve it. So let's see what the problem is. So the problem says a color. So in the picture, if you see the red box with dark border, this is the color, is sliding along the circular rod. So the circular black circle rod you can see in the picture is the circular rod, and the color is rotating along that circle. Now the problem says the circular rod in a vertical plane, meaning the circular rod is vertical, so there is no inclined plane, so it's just on a vertical plane. For example, XY plane. If the color has a speed of 5 meter per second, so the color, the red square here, that color is moving 5 meter per second. The velocity, which is 5 meter per second, is only valid at that point B, so at that instant. Since it has an acceleration, it will change, but at the current position at B, the velocity is 5 meter per second, as shown in the figure. So determine the acceleration. So the problem asks to find the acceleration and normal force of the rod on the collar. Since we know if something is rotating in a circular path, it will have a normal force. So what normal force the rod has on the collar at that instant, so at location B, and the question says assume the mass and spring undeformed spring length and spring constant is 1 kilogram 150 millimeter, and spring constant 100 Newton per meter. And it says also the neglect friction, so we don't have to worry about any friction. Okay, so let's start with our what is knowns. Mass is given 1 kilogram, K we know 100 Newton per meter, and we know the velocity of the color 5 meter per second. What are the unknowns? The problem asks us at what is the acceleration and normal force of the rod on the collar at position B. So let's draw a diagram. Since the collar is attached with this spring from this fixed position with the collar, so the spring is pulling the collar is this direction, but the collar is only can move along this direction. So exactly at this point there is a pulling force by the spring. So that is here the force pulling by the spring, which is proportional to the how much the spring is elongated from its original position. And it's given that the original length of the spring is 150 millimeters. So if we know the total length of the spring here, then we can know how much the spring is elongated at that position, and then we can use that to find the force at that location. And then there is always a weight of the collar that is downwards, so that is mass into gravitational acceleration, and there is a normal force acting from the circular rod to the collar, and this is the horizontal line. So this is our diagram. So now let's move to our solution. So first, if we try to find the solution, we can work. We know the length, which is undeformed length of the spring. So which is 150. But from the figure, we want to know what is the angle here. So from the figure, it says that the distance between A to C is 175 millimeter, and from C to O is 125. So the total length from here, from A to O, is 300. 175 plus 125. And we know since the diameter is the same, so CO is the radius of the circle, so OB will be the same, which is 125. So if I use 10 alpha, if we assume this angle is alpha, which will be same if I draw a parallel line. So this angle, if we assume this angle is alpha, meaning this angle alpha, then we can find from taking 10 alpha 125 over 300, and alpha is 22.62 degree. So we found this angle. So now we can apply summation of force. But before we apply the force, we need to know what is X, because that will give us the force on the spring. So how do we find the length of a spring at point B? AB. So if I use Pythagorean law here, Pythagorean law, this is 90 degree. So AB will be equals to square root of 300, which is AO, plus OB whole square, and square root all over. So if we do that, we find AB is 325. So meaning at position B, the length of the spring is 325 millimeter, and we know the original length of the spring is 150 millimeter. So we can find the spring extension, which is 325 minus 150 equals to 175 millimeter. So now we have X. Now we can work on the force. So now we're going to apply the Newton's second law of motion, equation of motion for normal and tangential coordinate. So we know for Newton's law, F equals to mass into acceleration. So we're gonna work on each direction at a time. So there is two direction, normal and tangential. So summation of force in normal direction will be equals to mass and then acceleration in normal direction. So so for force, we can have this x and y component of this force, but for acceleration, on the collar there is a two acceleration, which is, the normal acceleration component is always towards the center of gravity, so it will be this direction. And since the collar is moving this direction, so this tangential component, the tangent at that location would be this direction, which is this direction. So we know the acceleration of MAN, normal acceleration, and tangential acceleration would be in this direction. Okay, so let's solve. So summation of n. So in normal component we have only this we know this is alpha. So we want this component of this force F. So F equals to kx and sine alpha, because this is angle alpha and we want this force, so sine alpha, plus normal, so it is in upward direction, so this is positive, so we're doing this direction positive, this direction positive, so yeah, and then normal, and then we know the weight, right? Weight is acting downward, So this weight is acting downward, so it's negative. And on the other side, we have only the normal acceleration, mass acceleration upwards, so it's positive, so mn. So this is our equation. If we plug those values, k equals to 100, x that we find 175 millimeter, if we convert to meter, 0.175 millimeter, and sine alpha is sine 22.62 and plus n, and then we know mass is 1 kilogram, so that's 1, and z 9.81 meter per second square, so that's that. We know that n, normal acceleration component from our previous chapter, is velocity square over rho. Rho is the distance from center to the path, which is the circular path. So if we plug that value, v we know it's given 5 meter per second, and rho would be 0.125 meter. So if we apply that, and we can solve for n, which is 203 Newton. So this is the normal from the collar to the from the rod to the collar. So this is one of our answer that we're looking for. Now we need to work on the tangential part of the force. Again, we have only in the tangential part we have only this force component. So this is alpha, so we'll have cos alpha. So cos alpha kx is the same in mat. So this is the acceleration part of this equation of motion. So if we plug the value divided by m, so k equals to 100, x, we put the value, and if we solve, we can get the tangential component of the acceleration is 16.15 meter per second square. Now it's easy to solve from here. So how do we find, because our another goal to find the acceleration at point B. So how do we find the magnitude and direction of acceleration at point B? So to do that, it's simple. The acceleration at point B will be equals to, so a b is equals to the tangential component and normal component whole square. Let me make that right. So whole square 2, so at square over n plus an square, and then a square root all over it. So if we do that, plug the value, and we can find the acceleration, magnitude of the acceleration at point B is 200.65 meter per second square. Now how do we find the angle? We can assume that angle is b, beta. So tan beta we can find, so this is our normal direction in tangential direction. So if we take the normal component, which is 200 an, so we took that in the top part, so 200, and we take the tangential component in the bottom, so we got the 85.38. So this will be our direction of acceleration AB, and we found this angle beta is 85.38. So we have found our normal force that acting from the rod to the collar, and we will also find the acceleration, magnitude, and direction. So we have solved the problem. So in next class we're going to solve another example. There will be a third example for Newton's second law of motion, and then we're going to move to next chapter. So in next problem, example 3, we're going to use cylindrical coordinate to solve a problem. Till then, thank you. See you.